Now that we've come up with the definition for momentum as the product of mass times velocity, and that we've established that momentum for a closed system is a conserved quantity, or the total momentum before and after a collision are equal, and since we've looked at Newton's second law in terms of momentum, we're going to take a look at the specific behavior of objects and the forces involved in collisions, and we're going to take a look at a new term that we call impulse. Collisions aren't just for cars. If you're anything like me, when you think of a collision, you often think of a car crash, but there's all sorts of examples of collisions in our day-to-day life. When a tennis racket and a ball make contact, that's a collision. Likewise with a baseball bat and a ball, or billiard balls, or a hammer hitting a nail. All of these and any other contact is an example of a collision, and we should be able to take a look at them through the concept of conservation of momentum, and now through collisions and impulse. So the first thing that we want to consider is that when collisions happen, the forces of the two colliding objects are usually so much greater than any other forces from external objects that we can ignore the external forces and focus just on the forces of collision. And we have a slight intuition for this from the time of being very young. Imagine any 6-year-old playing with two toy objects, and these two toy objects are obviously flying through the air, moving toward each other to attack. And what happens? At the moment of collision, we show a conservation of momentum. This momentum direction and this momentum direction change, and they move off with a conserved momentum. And it's not until after that moment of collision, when the two objects are moving away, that then we start to consider, well, what effect does gravity have on these two crazy flying objects that have now been knocked unconscious by their impact? Well, now they're going to move off in a parabolic path and hit the ground. I've seen my own nephew play this very same game, and that demonstrates conservation of momentum very well. But it is an intuition that we have, and we can say that that is true. That during a collision, since those forces of the two objects colliding are so much greater than the other outside forces, we can consider it a closed system, we can consider momentum conserved, and we can say that the average force in that situation is the force of the collision. Alright, so that's a closed system for the duration of the collision, and that's a very short duration. Remember, when you have your two toy objects flying through the air until they crash, there's the moment of their collision where we say that that force is the greatest force, but once they're no longer colliding with each other, now the most significant force are the external forces, like gravity, that causes them to crash to the ground. So that's only true, or we can only consider momentum a conserved quantity during the moment of collision, and those times are often times less than a second, a fraction of a second, a thousandth of a second, a nanosecond. When two ordinary objects collide, in general, they're usually deformed, usually considerably deformed. Take a look at some of the slow motion videos that are attached in this assignment, and you'll be able to see different examples of deformity during collision. But the deformity that occurs when two objects collide is because of the massive forces that are involved during the collision, and those massive forces are the collision forces. They're Newton's third law, equal and opposite on both objects. So let's consider what happens during a collision, that very small time frame. First thing is that before the two objects collide with one another, the force is 0. And then throughout the moment of the impact, which is very small, the force jumps from 0 to a very large number, and then as the objects move away from each other, they're going to return back to 0. And so we could demonstrate that change by looking at a force over time chart for your average experience of having a collision. On this graph, we have our y-axis is given by force, and our x-axis is time. So at the very initial moment of collision, the force starts at 0. As the two objects move toward each other and deform significantly, the force shoots up in an exponential fashion. And then at the very top, as the objects release their contact from one another, the force will shoot back down to 0. Remember that if we're going to consider this, the force over time, that interval of time is actually very, very small. And according to Newton's second law, the net force that an object experiences is going to be equal to the momentum over time, or the rate of change of momentum. And what we also assume is that the net force that matters during a collision is actually just the force of collision, because we said that those other outside forces are so small that we're going to neglect them. If I rearrange this equation right here by multiplying both sides by time, then I get this, which is just a rework of Newton's second law. And it says that force times the change in time will be equal to the change in momentum. And here is our new term. In that equation, force times the change in time is equal to the change in momentum. You have this new term called impulse. And impulse is just the product of a force times the time interval over which that force was experienced. The units of this are newtons times seconds. And here's a neat thing about those units is momentum is kilogram meters per second. And if we divide that by another change in time, then you get kilogram meters per second squared, which is equal to 1 Newton. So that means that if I multiply kilogram per meter times meters per second squared, which is force, times a time interval seconds, then you end up getting, hey look, kilogram meters per second again, or a Newton times a second. That means that we can say for all constructive purposes that 1 Newton second is equal to, in every single way, 1 kilogram meter per second. And that's the impulse. And impulse changes momentum. You take a look at that equation and you can see that F times force times the change in time is equal to the change in momentum, then that must mean that if there is an impulse, then the momentum will change. And since we see that this is an equivalency, they're actually equal to each other, not related. This is not a proportion. That means that the magnitude of the impulse, or the amount or value that we get as the product of force times time, is going to be equal to the amount of change that we experience for momentum. Since the force during the impact isn't usually constant, we can't use our typical dynamics equations and we can't use our typical work equations to solve. In fact, if you take a look, during a collision, right, this is definitely the very definition of a variable force. So the best we could do during a collision is to calculate over that time interval what was the average force experienced. And you could do that by finding the overall integral area under the curve. But we could also just approximate the force experienced for that time as the average force. And if we did that, then the force experienced over time, or the average force, would be represented by this line here. And that's equal to the actual impulse. The area under this curve would be equal to the actual impulse experienced by the object. So let's go ahead and let's take a look at some example calculations. What we're going to be doing is we're going to be calculating the impulse of a Benny that has a mass of 70 kilograms as he lands on the ground, and in doing this we're going to be comparing the impact, the force impact of bending your knees when you land versus landing straight leg. So we're actually going to be comparing the forces of a straight leg land versus a knee bend land, and we're going to be looking at that in terms of impulse as it relates to change in momentum. So what do we need to do to make this happen? Well, in order for us to analyze the situation, we have to take a look. A 70-kilogram Benny is landing on firm ground, and it's from a height of 3 meters. So he jumped from 3 meters. We're assuming that his initial velocity in that situation was 0 meters per second. So we can use step one, we can use kinematics to solve for the velocity that Benny had right before impact. Because what happens is right before impact he had velocity. At the end of the impact he was at rest on the ground. So we're going to use the kinematic equation. Final velocity equals initial velocity plus 2ax, and I guess we could say that that's y in that situation. And since the initial velocity was 0, he jumped from rest, then that means that the velocity that Benny had right before he hit the ground is going to be equal to the square root of 2 times 9.8 meters per second squared. That's the acceleration due to gravity. And then we assume that when Benny lands stiff-legged, his body only moves 1 centimeter downward during impact. So that means that, we're looking at his velocity, which was he jumped from a 3-meter height, so that's going to be times 3.0 meters. And when I solve that, 2 times 9.8 is 19.6 times 3, take the square root of that, and I get 7.7 meters per second. That's Benny's velocity the moment before, or the moment of, his impact. So now we have that velocity, and now we can consider change in momentum. Change in momentum is final minus initial. And since Benny's mass doesn't change, he stays 70 kilograms the whole time. That's going to be mass times final velocity minus initial velocity. And in that case, we started with an initial velocity during the impact. We started with that initial velocity of 7.7 meters per second. And his final velocity at the end of the impact, well, he wasn't moving anymore, and that's 70 kilograms. One of the things that you're going to notice when you solve this problem is that you get a negative value. Your change in momentum is negative 540 newtons times seconds. So that means that this is the impulse that Benny experienced when he landed on the ground. And this impulse is the same whether he landed stiff-legged or bent knee, because whether he's landing stiff-legged and only moving 1 centimeter during his land, or whether he's landing bent knee and he's moving 50 centimeters, the impulse is the same, because no matter what, the land makes him move his velocity from 7.7 meters per second to 0 meters per second. So that means his change in momentum is the same. So his impulse is the same, negative 540 newtons times seconds. So let's consider what we know here. We know that because the sign is negative, that means that the change in momentum was to slow it down. So that means that the force that was applied was opposite the direction of the momentum. The direction of the momentum in this problem is downward. So that means that the force and the impulse that Benny experienced is upward. This upward force has a value, and we can actually solve for the upward force value by figuring out the time, because remember that impulse is force times time. So if we have that impulse, it's negative 540 newtons per second, then we can solve if we have time. And we can solve for time using kinematics. So step 3, solving using kinematics, I'm going to be using displacement equals 1/2 v plus v naught times time, which is just one of our kinematic equations, and that's actually a y value there. And his movement was 1 centimeter, so 0.01 meters, times 2 divided by the average, or 1/2, 7.7, which is, in this case, 3.9 meters per second. And that will equal time, and our time in this situation, 0.01 times 2 divided by 3.9, is 2.6 times 10 to the negative third seconds. So I can now plug this into this equation, and I can get that the force that Benny experiences is 540 newtons per second Newton seconds divided by 2.6 times 10 to the negative third seconds equals 2.1 times 10 to the fifth newtons. That's an extremely large amount of force, and that's the force of the ground on him during his land. Now we're going to bring it back and we're going to think about his average force, right? Because Benny's actually, if you think about it, the average force is going to be equal to the force from the ground, which we just calculated, minus his gravity, and that should have an actual numerical value. So in order for us to figure out the force that the ground actually experienced as a result of his land and the ground, we've calculated the average force. So now to figure out the force on the ground, you could take the average force plus mg, which is Benny's weight, and average force is 2.1 times 10 to the fifth newtons. Add Benny's weight, which is 70 kilograms times 9.8, or 690 newtons. You're going to notice 2.1 times 10 to the fifth is hundreds of thousands, and this is just a couple hundred, so you actually still get 2.1 times 10 to the fifth newtons as the force that Benny experienced when he landed straight-legged. So that's the force of the ground on his legs when that occurred. This does reinforce that we consider the average force equal to the force of impact, because even though we had to add his weight back in to actually see what the force that the ground applied to Benny was, we saw that it made very little difference in our overall number. So our assumption that external forces were relatively pointless or relatively non-impactful ended up being right. So that's the force of landing stiff-legged. Now we can go back and look at the force that Benny experienced when he landed with bent knees. And the nice thing here is that a lot hasn't changed. The velocity that he had upon impact is still 7.7 meters per second. He still comes to a complete stop. So his change in momentum is still 540 newton seconds in the downward direction, and that's still his impulse. His impulse is not changed. What has changed is the time interval, because instead of falling for just 1 centimeter, he fell for 50 centimeters. So we can rearrange our equation that solves for the average time, and we say that the time is going to equal 2 times his displacement, which is 50 centimeters, and then we're going to have 7.7 meters per second. So the time it took him to land 50 centimeters, or 0.5 meters, instead of falling for just 1 centimeter, is a lot longer. It took him 0.13 seconds to cover that displacement over that change in velocity. And if you look at 2.6 times 10 to the negative third versus 0.13 seconds, we're looking at 1,000th of a second versus 1/10 of a second approximately. So we can already have this assumption that the force is going to be much less when he bends his knees. Now we can use this time to figure out exactly how much less it was. And we do that by saying that force equals change in momentum, which was negative 540 newton seconds, divided by the change in time, which is 0.13 seconds. And you get that the average force experienced was 4.2 times 10 to the third newtons. And just as we assumed, 4.2 times 10 to the third is a lot less than 2.1 times 10 to the fifth. We're magnitudes off. But again, this is the average force, so now we're going to see, well, how much of a difference does it make that there's this external force of gravity working? We say the average force is going to be equal to the upward force of the ground minus Benny's weight. So we solve for the force of the ground, which equals the average force, which we just calculated, plus mg, so that's going to be 4.2 times 10 to the third newtons, plus 690 newtons. And here we actually see a small change in the mass because we've reduced the force by so much. So we see that the force that the ground exerted in this situation is actually 4.9 times 10 to the third newtons, which is still a much, much smaller number than our 2.1 times 10 to the fifth newtons for landing straight-legged. Here we have 210,000 newtons, here we have 4,900 newtons. If you think about the difference between that, it's actually so notable that the force on the feet and the force on the legs is less in the bent knee situation, to the point that your legs and the structural integrity of your legs is actually not enough to experience this force. So landing straight-legged in this situation would more than likely result in some sort of a fracture of the bone. And that's why when you land, you always bend your knees instead of landing straight-legged. And if you ever do accidentally land straight-legged, even from very short up distances, severe damage to your tissue and bones will occur.